Close your eyes for a moment and try to imagine a world that has never known a human footstep. There are no roads, no cities, no fields of wheat, nothing carved or built or named. There is only the planet itself, breathing, turning, alive with sound in ways we have nearly forgotten how to hear. The air in this world is thick and warm and rich with oxygen. It smells of wet earth and rotting wood, of resin and pollen and the salt breath of ancient seas. The sky is enormous, unpolluted, and at night it blazes with stars so numerous and brilliant they cast faint shadows on the ground below. And from the forest, if you could call it a forest, this vast, world-spanning cathedral of vegetation unlike anything living today, comes a constant low music. The buzzing of insects, the calling of strange birds, the deep resonant bellowing of creatures so large that the ground shivers faintly when they walk. This is the world as it was 66 million years ago, and it is about to end. The age of the dinosaurs had been extraordinary by any measure. For over 160 million years, the great reptiles had ruled the land, the skies, and the shallow seas. To put that number in perspective, the entire history of our genus, Homo, spans perhaps 3 million years. The dinosaurs had been dominant for more than 50 times longer than that. They had survived ice ages and volcanic catastrophes. They had diversified into thousands of species across every continent. They were, by every measure of evolutionary success, the most accomplished large animals the planet had ever produced. And yet, on one ordinary morning in the late Cretaceous period, everything changed, not slowly, not across millennia, but in a single shattering instant. It began as a point of light in the pre-dawn sky, brighter than any star, growing with terrifying speed. A rock roughly 12 kilometers across, wider than many cities, larger than Mount Everest measured from base to peak, was plunging through Earth's atmosphere at roughly 20 kilometers per second. It had traveled for billions of kilometers across the void of space to arrive at this precise moment, at this precise coordinate in the Gulf of Mexico. The impact, when it came, defied any ordinary scale of violence. The energy released in that first fraction of a second was equivalent to roughly 10 billion of the most powerful nuclear weapons ever built by human hands. A fireball expanded outward faster than the speed of sound. The shockwave flattened ancient forests for thousands of kilometers in every direction, as completely as if they had never existed. The rock itself plunged through the crust and into the mantle, and the resulting crater, the Chicxulub crater, as geologists now call it, measured roughly 200 kilometers across. But the immediate explosion, as catastrophic as it was only the opening act. Within hours, billions of tons of rock and dust and vaporized material had been flung into the upper atmosphere, where it would remain suspended for months, perhaps years. Enormous amounts of sulfur dioxide billowed into the stratosphere, where it combined with water vapor to form a reflective haze of sulfuric acid droplets that blocked the sun's light with extraordinary efficiency. The sky darkened. Temperatures, which had been warm across much of the planet, began to plunge. In some regions, the drop may have been as dramatic as 15 or 20 degrees Celsius within a matter of weeks. Without sunlight, the planet's plant life, the foundation of almost every food chain on land and in the oceans, began to die. First the smaller plants, then the great forests. As the plants collapsed, the herbivores that depended on them began to starve, and as the herbivores failed, the predators that fed upon them followed. It was a cascade, an unstoppable unraveling of the web of life, moving from the bottom up. Within a geological heartbeat, perhaps as little as 76,000 years, a number so small it barely registers in the 4 billion-year history of our planet, 3/4 of all species on Earth had gone extinct. This was the 5th mass extinction event in Earth's long history, and it would prove to be the most consequential for the future of everything that came after. The non-avian dinosaurs, every single lineage, from the colossal sauropods whose necks arched above the treetops like living cranes, to the horned ceratopsians, to the armored ankylosaurs, to the swift and terrible theropods, were gone. The sky-ruling pterosaurs vanished. The great marine reptiles, the mosasaurs and plesiosaurs that had patrolled the warm Cretaceous seas, disappeared into the sediment record that would one day tell their story to curious paleontologists. The world fell quiet in a way it had not been quiet for 160 million years. But not everything died, and in the story of what survived and why lies the beginning of the most extraordinary tale of recovery and reinvention that this planet has ever witnessed. Certain animals, through a combination of luck, physiology, and the peculiarities of their ecological situations, endured. Crocodilians made it through, their remarkable metabolisms allowing them to survive for months without food. Sea turtles persisted. Many freshwater fish survived. And crucially, the avian dinosaurs, the birds, managed to hold on. Their ability to fly, to range widely in search of food, and their capacity to eat seeds, which can survive in the soil for years, gave them a lifeline through the darkness. But the survivors that matter most to this story were the smallest and least glamorous of all the Cretaceous fauna. Deep in their burrows, pressed into crevices in the rock, huddled in the darkness of the forest floor, the mammals waited. They had been waiting in evolutionary terms for over 160 million years, a long, patient vigil in the shadows of creatures far larger and more powerful than themselves. They were warm-blooded, which meant they could stay active even as temperatures fell. They were small, which meant they needed very little food to survive. Many were nocturnal, already adapted to operating without sunlight. And many were omnivorous, capable of eating insects, seeds, roots, fungi, whatever the shattered world still offered. As the dust slowly began to settle, as the first faint stirrings of photosynthesis returned to the devastated landscape, these small animals emerged from their hiding places into a world that was ruined, empty, and absolutely full of possibility. The age of mammals had begun. Imagine standing on the surface of the Earth in the first years after the impact. The landscape around you is unlike anything that exists in our world today. The ground is grey and white, covered in a deep layer of ash and impact debris that has settled from the sky over months of darkness. The great forests are gone, reduced to charred stumps and fallen trunks, slowly being colonized by the first brave pioneers of recovery, mosses, ferns, and fungi, the organisms that always come first when catastrophe has scoured a landscape clean. The sky above is a strange, muted color, not quite gray, not quite brown, filtered through a haze of particles that still lingers in the upper atmosphere. Sunlight reaches the surface, but it has the quality of a perpetual overcast day, pale and directionless. The air is cold, the silence is enormous. And then from a crack in the base of a fallen log, a small nose appears. Two bright eyes blink in the strange dim light. A creature the size of a rat steps cautiously into this new world, sniffing the air with rapid, nervous movements. It is not impressive to look at. It has no great horns, no terrifying claws, no armored hide. What it has in abundance is adaptability. This creature, or something very much like it, is the ancestor of everything that follows in our story. Every elephant and whale, every bat and lion, every monkey and horse and human being traces its lineage back to something like this. A small, warm-blooded, opportunistic survivor picking its way through the ruins of the Mesozoic world. The single most important biological trait that these animals possessed was endothermy, the ability to generate their own internal body heat. We take this for granted because we are warm-blooded ourselves, but it is worth pausing to appreciate what a profound advantage this was in the cold, sunlight-starved world following the impact. Reptiles, the dominant vertebrates of the Mesozoic, are ectotherms. They depend on external heat sources to regulate their body temperature. On a cold, dark morning with no sun to warm the rocks, a reptile becomes sluggish and eventually helpless. But a mammal burning food to generate internal warmth remains active, alert, and capable of hunting. Warmth, however, comes at a cost. Maintaining a constant internal temperature requires a great deal of energy, far more than a cold-blooded animal of equivalent size needs to consume. This is why mammals must eat so much more frequently than reptiles. But in the immediate aftermath of the extinction, this was actually an advantage rather than a burden. It drove the early mammals to explore every possible food source relentlessly, which in turn made them extraordinarily flexible in their diets. The second great mammalian advantage was the nourishment of young with milk. This seemingly simple behavior had profound implications. Unlike the eggs of reptiles or birds, which once laid are left largely to fend for themselves, mammalian young are born into a relationship of intense physiological dependence on their mothers. A mammal mother does not merely produce an offspring and hope for the best. She carries it internally, nourishes it through the placenta, gives birth to it alive, keeps it warm with her own body heat, and feeds it with milk, a food source so nutritionally complete that a blue whale calf can gain as much as 90 kilograms per day on milk alone. This investment in each individual offspring is costly, but it produces animals that arrive in the world better prepared, better fed, and better protected than the young of any reptile. Even in a devastated landscape, a mammal mother was giving her offspring every advantage she could. As the Paleocene epoch unfolded across its 10 million years, from 66 million years ago to about 56 million years ago, the mammals began to change. The world was slowly recovering. Ferns gave way to flowering plants, low shrubs became thickets, thickets became forests, and as the food supply diversified and expanded, the mammals diversified with it, filling the ecological niches left vacant by the extinct dinosaurs. The earliest Paleocene mammals were still remarkably similar to one another, small, generalized creatures that scientists describe collectively using terms like archaic ungulates or condylarths. They were the raw material from which everything would be sculpted, but already the first hints of differentiation were appearing. Some lineages were becoming slightly larger, some were developing teeth better suited to plant material, some were spending more time in the trees. One of the first great mammal radiations of the post-extinction world was the ancestors of the even-toed ungulates, the artiodactyls, which would eventually give rise to deer, cattle, pigs, camels, and ultimately whales. Their earliest representatives were unassuming creatures, nothing like the magnificent animals their descendants would become. But they were already specializing, teeth adapted for tougher plant material, legs growing slightly longer, digestive systems beginning the long evolutionary journey toward rumination. Meanwhile, in what is now South America, which at this time was an island continent, drifting slowly away from Africa, a completely separate mammal community was evolving in isolation. The South American mammals were developing their own unique solutions to the problems of survival. Giant rodents, armored glyptodonts, ground sloths, and a bizarre group called the notungulates, which would independently evolve body forms remarkably similar to horses and rhinoceroses, despite being entirely unrelated to either. The lesson of the early Paleocene is one of the most important in all of evolutionary biology. Given empty niches and enough time, life will fill them. The ecological roles vacated by the dinosaurs were not left empty for long. The mammals rushed in not consciously, not deliberately, but driven by the blind and relentless logic of natural selection, which rewards any variation that confers even the smallest advantage in any available environment. The world had been broken open, and the mammals, small and warm and adaptable, were pouring through every crack. 56 million years ago, the Earth experienced one of the most dramatic and rapid warming events in its geological history. Scientists call it the Paleocene-Eocene thermal maximum, or PTM, and it unfolded over just a few thousand years, a blink of geological time. Vast quantities of carbon dioxide were released into the atmosphere from volcanic activity and the melting of methane hydrates on the seafloor, and global temperatures rose by as much as 8 degrees Celsius above the already warm Paleocene baseline. The result was a world so warm that it barely resembles the one we inhabit today. The poles were ice-free. Palm trees and crocodilians lived within what is now the Arctic Circle. The equatorial tropics were almost unbearably hot and humid, a permanent steaming sauna of vegetation so dense and so complex that it would take a human explorer years to properly traverse a single square kilometer of it. The forests of the Eocene epoch were the richest and most diverse terrestrial ecosystems the planet had ever seen. And in those forests, something remarkable was happening. The flowering plants, the angiosperms, were completing one of the most spectacular evolutionary radiations in the history of life on Earth. Flowering plants had first evolved in the early Cretaceous, but they had spent much of the Mesozoic era as relative underdogs, competing with the ancient forests of ferns and conifers and cycads. Now in the warm, wet Eocene, they were taking over. Everywhere you looked, flowers were opening in the canopy, in the understory, on the forest floor, on the riverbanks and lake shores. And with the flowers came fruit. Fruit is, in a very real sense, one of the most cunning evolutionary inventions in the history of life. A fruit is a bribe. The plant packages its seeds inside a nutritious, sugar-rich, brightly colored package and offers it to any animal that will eat it and carry the seeds away. The plant benefits because its seeds are dispersed, sometimes kilometers from the parent tree. The animal benefits because it gets a meal. Both parties win, and this elegant arrangement, repeated trillions of times across millions of years, drove the co-evolution of plants and animals in spectacular and interdependent directions. For the mammals, fruit was a game changer. Here was a food source that was abundant, nutritious, and crucially required a new set of skills to find. Fruit hangs in the canopy. It is often hidden among leaves. It ripens at different times in different places. Finding it requires good eyesight, the ability to move through a three-dimensional environment, and the memory to track which trees are bearing fruit at any given time. The animals best equipped to exploit this resource would thrive, and one group of mammals already spending time in the trees was about to undergo a transformation that would ultimately lead 60 million years later to us. The primates. The order primates first appears in the fossil record in the early Eocene, though their origins likely stretch back into the late Paleocene. What distinguished the earliest primates from other small arboreal mammals was a suite of characteristics that, taken together, represent one of the most consequential evolutionary packages in the history of vertebrate life. Their eyes had shifted to the front of the face, providing stereoscopic three-dimensional vision essential for judging distances when leaping between branches. Their hands and feet had developed grasping digits, often with flattened nails rather than claws, and their brains, relative to their body size, were larger than those of comparable mammals, with particular expansion of the regions associated with visual processing and fine motor control. These features, the grasping hand, the forward-facing eye, the expanded brain, evolved in the service of life in the trees. They were solutions to the very specific engineering problem of being a medium-sized animal in a complex three-dimensional environment, trying to pick small fruit from thin branches while avoiding predators. And yet these same features would prove to have applications far beyond any forest canopy. The grasping hand that evolved to pick fruit would eventually make tools, paint cave walls, and write symphonies. The brain that expanded to track ripening trees would eventually map the cosmos. The Eocene world was also witnessing the dramatic early diversification of the bats. The earliest known bat, a creature called Onychonycteris, dates to approximately 52 million years ago, and it was already a fully capable flyer. The wings, the elongated fingers, the modified shoulder girdle were all in place. How flight evolved in bats remains one of the great unresolved questions in vertebrate paleontology. Did bats evolve flight from the ground up, beginning as running animals that leapt into the air, or from the trees down, beginning as gliders? We don't yet know. But what is certain is that once bats became capable of powered flight, they radiated explosively into one of the most successful mammal orders in history. Bats occupy an ecological niche that no other mammal had ever exploited, the nocturnal aerial insectivore. By flying at night and hunting insects on the wing, the earliest bats faced essentially zero competition from any other vertebrate. The skies after dark were theirs. And many lineages of bats evolved echolocation, the ability to emit high-frequency sound pulses and interpret the returning echoes to build a detailed three-dimensional map of their surroundings, with such extraordinary precision that a bat can detect and catch a mosquito in total darkness. By the late Eocene, roughly 34 million years ago, the great warmth was ending. Antarctica had been drifting southward, and as it moved into the polar position, the formation of a new ocean current, the Antarctic Circumpolar Current, began to isolate the continent from the warming influence of tropical waters. Sea ice began to form. Ice sheets slowly accumulated on the continent. The global temperature began its long, slow descent toward the cooler world we inhabit today. The greenhouse forests of the Eocene began to fragment and shrink. A new chapter was opening. But before we follow the story into the cooling world of the Oligocene, it is worth pausing to appreciate what the Eocene had achieved. In its 30 million years, from 56 million to 34 million years ago, the mammals had exploded in diversity. The ancestors of every major mammalian order alive today had appeared. Horses, tapirs, and rhinos had begun their separate journeys. The first true carnivores, the ancestors of cats, dogs, and bears, had appeared and begun to diversify. The great whales were already swimming in the warm Eocene seas, and in the canopies of the equatorial forests, a small, fruit-eating, big-eyed primate was looking out at a world that, 60 million years hence, its descendants would attempt to understand. The world that emerged from the cooling of the late Eocene was fundamentally different from the warm, forested planet that had incubated the early mammal radiation. Temperatures had dropped significantly. Rainfall patterns had shifted. The great equatorial forests that had blanketed much of the planet began to shrink toward the tropics, replaced in the mid-latitudes by open woodland and scrubland. And then slowly at first, and then with gathering momentum, the grasslands came. Grasses, members of the family Poaceae, are among the most successful plant families ever to evolve. They are almost indestructible. Unlike a tree which can be killed by being cut or burned, a grass plant stores the bulk of its energy and living tissue underground, in its root system and its growing point at the base of the stem. You can graze it, burn it, freeze it, or trample it, and it will come back. This resilience, combined with the ability to thrive in the drier, more seasonal climates that were spreading across the mid-latitudes, gave grasses an enormous advantage over the forest plants they were replacing. By the Miocene epoch, which began about 23 million years ago, grasslands had become one of the dominant ecosystems on Earth, covering vast swathes of Africa, Eurasia, and the Americas. And their spread set in motion one of the most dramatic episodes of evolutionary change in the history of mammals. The problem with grass from an animal's perspective is that it is extraordinarily tough to eat. The leaves of grasses contain microscopic crystals of silica, essentially tiny fragments of glass, called phytoliths, which are embedded in the plant tissue to deter grazers. When a mammal eats grass, these silica crystals act like sandpaper on the teeth, grinding them down from the outside in. An animal that relied on the soft, rounded teeth suited to eating leaves and fruit could not survive on a diet of grass. Its teeth would wear away and it would die. The evolutionary response to this challenge is one of the most beautifully documented examples of natural selection in the entire fossil record. Across dozens of separate mammal lineages, horses, rhinos, cattle, deer, elephants, and many others, the same solution appeared independently: high-crowned teeth. Instead of the low, rounded, quickly worn cusps of a browser, these animals evolved tall, complex tooth crowns with deep ridges and valleys of hard enamel, which could withstand years of abrasive grass grinding before wearing down to the gum. Paleontologists call this condition hypsodonty, and its appearance in the fossil record tracks the spread of grasslands with remarkable precision. The story of the horse illustrates this transformation with particular clarity. The earliest horse ancestor, a creature called Hyracotherium, sometimes still referred to by its older name, Eohippus, lived about 55 million years ago and was about the size of a medium dog. It lived in the forests of North America and Europe, browsing on soft leaves and fruit. It had 4 toes on its front feet and 3 on its hind feet, each tipped with a small hoof-like structure. Its teeth were low-crowned, suited to soft vegetation. Over the following 50 million years, the horse lineage responded to the spread of grasslands in ways that were recorded in extraordinary detail in the rock strata of North America. Body size increased. A larger animal can travel further between food sources and is better able to defend itself on open ground. The side toes were progressively reduced until only the middle toe remained, the single large hoof of a modern horse, which functions like a natural running shoe, offering speed and endurance on hard ground. And the teeth became dramatically taller, more complex, and more durable. But the horse story also illustrates an important truth about evolution that is easily lost in simplified accounts. Evolution is not a straight line. The horse family was not a single lineage progressing steadily from small to large, from many-toed to single-hoofed. It was a rich, branching bush of dozens of species, many of which went extinct without leaving descendants. At various points in the Miocene, there were multiple species of horses living simultaneously in North America, each occupying slightly different ecological niches. The one-toed, large-bodied modern horse that we know is simply the last surviving twig of a once extraordinarily diverse family tree. The spread of grasslands also drove the evolution of the predators that hunted the grazers. In a world of open plains, where a prey animal can see a predator approaching from far away, the evolutionary pressure for speed was enormous. The swift, cursorial predators, the ancestors of modern cheetahs, wolves, and hunting dogs, were honing their abilities in an arms race with increasingly fleet-footed prey. At the same time, the grasslands favored predators that could cooperate, that could work together to bring down prey far larger than any single individual could manage alone. The social predator, hunting in coordinated groups, was becoming one of the dominant forces in open country ecosystems. And in Africa, in the Oligocene forest that still covered much of the continent, a group of primates was beginning to diverge into two lineages that would have enormous consequences for the future. The split between the Old World monkeys, the cercopithecines, and the apes, the hominoids, was occurring somewhere in this period, probably between 30 and 25 million years ago. These two lineages would eventually go in very different directions, the monkeys expanding to colonize environments from the tropical forest to the mountain snow line, the apes remaining more restricted but developing larger brains and more complex social structures, and from the ape lineage in a forest in Africa would eventually emerge the most consequential creature this planet has yet produced. Of all the stories that the fossil record has to tell, perhaps none is more astonishing, more almost impossibly improbable, than the story of how mammals returned to the sea and became whales. It is a story of transformation so radical, so complete, that it seems to challenge the very imagination. A four-legged, fur-covered, land-dwelling mammal, breathing air, giving birth on solid ground, somehow becoming a streamlined, ocean-going giant that never touches land again. And yet it happened, and we know in remarkable detail how. We must begin, as all whale stories must, in what is now Pakistan and northern India, roughly 50 million years ago. At that time, these lands were bordered by a vast, warm, shallow sea called the Tethys, an ancient ocean that has since largely vanished, squeezed out of existence by the collision of the Indian subcontinent with Asia. Along the shoreline of the Tethys, in muddy estuaries and river deltas, a medium-sized mammal was making its living. Scientists have named it Pakistus, and it is the earliest known ancestor of all the world's whales and dolphins. Pakistus looked nothing like a whale. It resembled in overall body plan something between a large dog and a small deer, 4 legs, a long tail, a narrow skull with eyes positioned high on the head. It probably walked along the shoreline and waded into the shallows to catch fish, using its strong, slightly webbed feet to navigate the muddy banks. Nothing about its outward appearance would have told you that you were looking at the ancestor of the blue whale. But inside the skull of Pakistus, there was a clue. The bones of its inner ear, the tiny, dense bones that transmit sound vibrations to the brain, had a distinctive thickened structure found only in the cetacean lineage. This feature, called the involucrum, is the single anatomical signature that identifies Pakistus and all its descendants as members of the whale family tree, regardless of how different they look from the outside. Even as the body was transformed beyond all recognition over millions of years of evolution, this inner ear structure remained, a deep fingerprint of ancestry. After Pakistus came a succession of transitional forms that document, step by remarkable step, the transformation from land to sea. Ambulocetus, the walking whale, lived about 49 million years ago and was clearly at home in both worlds. It had large, powerful hind limbs with paddle-like feet, and its spine had the kind of flexible, undulating movement that would eventually power the up and down tail stroke of modern whales. It could walk on land, though probably as awkwardly as a modern sea lion, and it could swim powerfully through shallow coastal water. Rhodhostus, living a couple of million years later, had gone further still. Its hind limbs were reduced, and its pelvis was only loosely connected to the spine. The connection that in land mammals rigidly links the legs to the body had begun to dissolve, freeing the spine for the powerful dorsoventral flexion of a swimming mammal. Its nostrils had shifted backward along the skull, beginning the long migration toward the top of the head that would eventually produce the blowhole. By 40 million years ago, the basilosaurids had appeared, and these were animals that only a paleontologist would recognize as anything other than sea serpents. Basilosaurus itself was a monster, up to 18 meters long, with a sinuous, almost serpentine body quite unlike the compact, streamlined shape of modern whales. Its front limbs had become true flippers. Its hind limbs, here is one of the most extraordinary details in all of paleontology, were still present, but tiny, functionless, and entirely unable to support the animal's weight on land. They were vestigial remnants of the terrestrial life of its ancestors, preserved by the slowness of evolutionary change even as everything around them had been utterly transformed. The transformation from Pakistus to Basilosaurus, from a land mammal to a fully aquatic one, had taken approximately 15 million years. In geological terms, this is very fast. In human terms, it is almost incomprehensibly slow. but the direction of change is unmistakable, recorded in rock after rock after rock, each fossil layer adding another chapter to one of the most complete evolutionary narratives in all of science. The whales that evolved from this lineage eventually split into two great groups, approximately 34 million years ago. The toothed whales, the odontocetes, retained the ancestral teeth and evolved the extraordinary echolocation system that allows species like dolphins, sperm whales, and killer whales to navigate, communicate, and hunt using sound alone. The baleen whales, the mysticetes, took a completely different approach, replacing their teeth with great curtains of baleen plates made of keratin that filter enormous quantities of small prey, krill, small fish, copepods from the water with each colossal gulp. It is the baleen whales that have achieved the most extraordinary feat in the history of animal life on Earth, the evolution of the largest animals that have ever existed. The blue whale, the largest of all, can reach 30 meters in length and weigh up to 200 tons. Its heart is the size of a small car. Its call, a low, resonant moan that carries for hundreds of kilometers through the ocean, is the loudest sound produced by any animal on Earth. And yet this magnificent creature, this leviathan of the deep, is the direct descendant of a wolf-sized, four-legged mammal that picked fish from the shallows of an ancient, vanished sea. Somewhere in the forests of Africa, roughly 20 million years ago, a group of primates was doing something that their monkey cousins were not. They were spending more time on larger branches, moving through the trees in a different way, arms above the head, body hanging vertically, reaching and swinging rather than running along branches on all fours. They were, in short, becoming apes, and the anatomical differences between an ape and a monkey, subtle as they might seem to the casual observer, would turn out to have consequences of cosmic significance. Apes lack a tail. This is the feature most people notice first, and it is genuinely significant. The tail of a monkey is a balancing organ, essential for the four-footed branch-running style of locomotion. Without it, apes are committed to a different movement style, one that emphasizes vertical posture, shoulder flexibility, and the capacity to hang, reach, and rotate the arms through a much wider range of motion. These are also, as it happens, precisely the physical features that would later allow human arms to throw a spear with accuracy, or draw a bow, or play a violin. The Miocene epoch, which lasted from about 23 to 5 million years ago, was the golden age of the apes. Fossil apes have been found across Africa, Europe, and Asia, a reminder that apes were once far more diverse and widespread than they are today, when only a handful of species survive. Among these Miocene apes were creatures that were experimenting with different ways of being a primate. Some were small and nimble, some were large and slow, some were committed to the canopy, others were beginning to spend time on the ground. For much of the Miocene, Africa was covered in forest. The equatorial belt of dense tropical woodland stretched across the continent in a great green band, and within it the apes thrived. But as the Miocene progressed and the climate became cooler and more seasonal, the forests began to fragment. The great continuous canopy broke apart, replaced in many regions by a mosaic of woodland, open savanna, and grassland. For the animals adapted to forest life, this fragmentation was a crisis. But for at least one ape lineage, it may have been the catalyst for one of the most important evolutionary developments in the history of vertebrate life. Around 7 to 10 million years ago, the precise date is still debated. The lineage leading to humans diverged from the lineage leading to chimpanzees and bonobos. The common ancestor of humans and chimpanzees was most likely a forest-dwelling ape, spending time both in the trees and on the ground. When the forests fragmented, the two lineages found themselves in different circumstances. One group remained in the retreating forest, continuing the ape way of life. The other found itself increasingly in the open, forced to cope with a world of grassland and scattered woodland. The great evolutionary innovation that the human lineage developed in response to this challenge was bipedalism, walking upright on two legs. We tend to think of bipedalism as an obvious advantage, but it is actually a very strange way to move. Walking on two legs is inherently unstable. We are, as one biologist memorably put it, controlled falling. A running human is perpetually on the edge of pitching forward. Our center of gravity is high, our base of support small, and our entire locomotor apparatus has been extensively remodeled from the four-footed architecture of our ancestors to achieve something that requires remarkable muscular coordination with every step. Why did bipedalism evolve? The most widely accepted hypothesis is that it freed the hands. In an open landscape, a primate that could carry food, fruit gathered from widely scattered trees, or animal protein from a carcass, back to a safe location had a significant advantage over one that had to eat where it found its food, vulnerable to predators. Bipedalism also raises the head above the grass, improving the ability to spot predators and food sources at a distance. And it is significantly more energetically efficient than knuckle walking for covering long distances, crucial in a landscape where food sources are far apart. The fossil record of human evolution is one of the most actively studied and debated in all of science, and new discoveries are made every few years that refine or revise our understanding of the family tree. What is clear is that by approximately 4 million years ago, the genus Australopithecus had appeared in Africa, small-brained bipedal apes that walked upright as their primary mode of locomotion, but had brains little larger than those of modern chimpanzees. The most famous individual is a female found in Ethiopia in 1974, named Lucy, who lived approximately 3.2 million years ago. Her skeleton, recovered in remarkable completeness, reveals a creature that combined a fully bipedal lower body with arms still long enough to suggest she also spent time in the trees. Lucy and her kind were not the ancestors of modern humans directly. The human family tree is far more complex than any single straight line, but they represent the kind of creature from which our own genus, Homo, would eventually emerge. And in the story of how that emergence happened, the evolution of a larger brain would prove to be the decisive development. About 2.6 million years ago, the Earth's climate system locked into a new pattern, one of the most dramatic and consequential shifts in the planet's recent history. The slow cooling that had been underway since the Eocene now accelerated into something far more extreme, a cycle of glaciations, massive ice sheets advancing from the poles and retreating again, each cycle lasting roughly 100,000 years, each one reshaping the face of the planet. At the peak of each glacial period, the ice sheets were extraordinary in their scope. A sheet of ice up to 3 kilometers thick blanketed most of Canada and extended deep into the northern United States. Much of northern Europe lay under ice. The sea level, with so much of the world's water locked up in ice, was more than 100 meters lower than it is today, exposing vast tracts of land that are now submerged beneath the ocean. The English Channel was dry. The Indonesian islands were connected to mainland Asia. Alaska was connected to Siberia by a broad land bridge, Beringia, across which animals and eventually people would migrate between continents. This was the Pleistocene epoch, and it was a world of extremes, brutally cold glacials alternating with warmer interglacials, each transition driving massive migrations and extinctions as species tracked their preferred climates across the landscape. But it was also, paradoxically, a world of biological abundance. The great grasslands and tundra that covered much of the ice-free land during the glacial periods, what scientists call the Mammoth Steppe, supported some of the largest and most spectacular land mammals that have ever lived. The woolly mammoth is the icon of this world, and deservedly so. These extraordinary animals, close relatives of today's Asian elephant, from which they diverged perhaps 6 million years ago, were superbly engineered for life in the cold. Their coat consisted of multiple layers, a dense, fine undercoat of soft wool, overlaid by a coarser layer of guard hairs that could grow up to 90 centimeters long, providing insulation equivalent to the finest Arctic clothing. Beneath the skin lay a layer of fat up to 10 centimeters thick. Their blood contained a modified form of hemoglobin that released oxygen more readily at low temperatures, a molecular adaptation to the cold that their warm climate relatives lack. Even their enormous curved tusks, which could reach 5 meters in length in the largest males, were functional tools for sweeping snow aside to reach the grasses and sedges frozen beneath. Mammoths lived in herds, almost certainly with the same kind of complex matriarchal social structure observed in living elephants. The oldest and most experienced female would have led the group, carrying in her memory the knowledge of where to find water in drought, which routes led through mountain passes, which seasons brought the richest grazing. When mammoths died, their companions showed behaviors that looked strikingly like mourning, lingering near the remains, touching them with their trunks, covering them with branches and earth. The mammoth was not alone in its grandeur. The woolly rhinoceros, larger than any living rhino, covered in thick reddish fur bearing two enormous horns, shared the mammoth steppe across Europe and Asia. Cave bears, the size of large grizzlies but more heavily built, hibernated in the caves of Europe, where their bones accumulated in extraordinary quantities. The cave lion, larger than any living lion, stalked the open tundra. The Irish elk, a deer, despite its name, found across Eurasia, bore the largest antlers of any animal that ever lived, spanning up to 3.5 meters from tip to tip. In North America, the Pleistocene megafauna was equally magnificent. Columbian mammoths, even larger than their woolly cousins, roamed from Alaska to Central America. American mastodons browsed the forests. Giant ground sloths, relatives of the modest two-toed sloths of South American forests, grew to the size of elephants. Glyptodonts, ancient relatives of armadillos, trundled through the undergrowth, their entire bodies encased in a dome of bone like a living tank. And the predators to match, Smilodon the saber-toothed cat, its enormous canines jutting like daggers below its jaw, the dire wolf, heavier and more powerfully built than any wolf alive today, the short-faced bear, the largest terrestrial mammalian carnivore in North American history. This was a world that human beings would eventually encounter, and when they did, it would change everything for the humans and for the megafauna alike. It was during the Pleistocene, against this backdrop of ice and giants, that our own species took its final shape. Homo sapiens, anatomically modern humans, appear in the fossil record of Africa by around 300,000 years ago, but for most of those 300,000 years, we were just one of several hominin species sharing the planet. Homo heidelbergensis roamed Europe and Africa. Neanderthals, our closest evolutionary relatives, occupied Europe and Western Asia, where they had been adapting to glacial conditions for hundreds of thousands of years. The Denisovans, known mostly from fragmentary DNA, occupied parts of Asia. For a time, multiple species of human were alive simultaneously on Earth. Then, sometime around 70,000 years ago, something shifted. Modern humans began to spread first across Africa, then out through the Middle East and into Eurasia, then into Australia, then across Beringia into the Americas. They brought with them something no previous animal had ever carried, a cognitive toolkit of extraordinary power. Language, symbolic thought, the ability to plan across multiple seasons, the capacity for cultural transmission of knowledge across generations. It was the most powerful evolutionary innovation since photosynthesis, and the world it encountered, the world of the Pleistocene megafauna, was about to pay the price. End of the last ice age was, for the megafauna of the Pleistocene, the beginning of the end. Around 14,000 years ago, the great ice sheets began their final retreat. The climate warmed. The mammoth steppe, the vast, cold, grass-dominated landscape that had supported the great herds, began to shrink, replaced by forest and wetland in the north and by expanding desert in some southern regions. For animals adapted to cold, open conditions, the warming world was becoming inhospitable. And yet climate change alone almost certainly cannot explain what happened next. Ice ages had come and gone many times during the Pleistocene. The mammoths and woolly rhinos had survived at least 5 or 6 previous glacial retreats. The ecosystems of the Pleistocene were not fragile, they had proved their resilience over millions of years. Something else was happening this time, something new had arrived. The coincidence is stark and to many scientists conclusive. Wherever modern humans arrived, the megafauna vanished. In Australia, the great marsupials, Diprotodon, the giant wombat relative, Procoptodon, the massive short-faced kangaroo, Thylacoleo, the marsupial lion, disappeared approximately 46,000 years ago, within a few thousand years of the first human footfall on that continent. In North America, the mammoths and mastodons and ground sloths and glyptodonts vanished between 13 and 10,000 years ago, coinciding with the spread of the Clovis people southward from Beringia. In South America, the pattern is the same. In Europe, where humans had been present for much longer, the process was slower, but the end result was the same. The animals that survived best were those with the longest history of living alongside hominins. In Africa, where our genus had been evolving and hunting for millions of years, the megafauna extinctions were comparatively modest. African elephants, rhinoceroses, hippopotamuses, giraffes, and the great variety of antelopes and zebras and wildebeest all made it through, because African animals had had millions of years to develop a healthy, appropriate terror of human hunters. They had evolved through hard experience across countless generations to run from the upright ape. But in Australia, which had known no large primate predator in its entire evolutionary history, the animals simply did not run. There was no instinctive fear. A giant wombat the size of a hippopotamus might stand and watch with curiosity as a group of human hunters approached. It would never have that chance again. The extinction of the megafauna was not simply a loss of large, magnificent animals, though it was certainly that. It was a restructuring of entire ecosystems, with consequences that ripple down to the present day. Large herbivores are what ecologists call ecosystem engineers. A mammoth trampling through a forest created clearings that allowed new vegetation to grow. Elephant-sized grazers maintained the grasslands by preventing the encroachment of shrubs and trees. Giant ground sloths dispersed the seeds of large fruits, avocados, Osage oranges, and others that had evolved to pass through the gut of a large animal. Without those dispersers, these plants were stranded, their evolutionary strategy of producing large, enticing fruit suddenly purposeless in a world without anything large enough to eat it. Ecologists have a name for these orphaned plants and the communities that depended on megafauna. They are called ecological anachronisms, living relics of a world that no longer exists, struggling to make sense of a landscape from which the key players have been removed. And yet life has always found a way to continue. The smaller mammals, the deer, the elk, the bison, the pronghorn, the wolves and coyotes and foxes, survived and even expanded, filling some of the ecological space left by the lost giants. In some regions, the extinction of megapredators allowed prey populations to explode, restructuring plant communities and creating entirely new ecological dynamics. Pleistocene extinction was a tragedy, a loss of biological diversity that we can only partially reconstruct from bones and frozen remains in cave paintings. But it was also, viewed from a long perspective, another chapter in the endless story of change that has characterized life on Earth since its beginning. Loss and renewal, extinction and radiation, the closing of one door and the opening of another. The mammals had survived the asteroid. They had survived the ice ages. They would survive this too. But the world they were inheriting was changing faster than at any previous point in their 66-million-year history. And the agent of that change was not an asteroid or a volcanic winter or a shifting climate. It was a primate, barely 1,000,000 years old as a species, whose extraordinary brain had given it the ability to remake the world around it in ways that no creature had ever managed before. There is a thought experiment that can help us understand the strangeness of the world we live in. Imagine visiting Earth from space 40 million years ago. You would see a planet covered in diverse forests, its seas teeming with life, its continents populated by a spectacular variety of large mammals living in something close to ecological equilibrium, predators and prey, plant eaters and the plants they eat, all locked into the complex, self-regulating dance that ecologists call a food web. Now come back to the present day and look again. The planet is the same size, the same sun shines on it, but almost everything else has changed, and a single species is responsible for most of that change. The transformation began slowly with the domestication of animals. This process, one of the most consequential in the entire history of mammalian evolution, started approximately 15,000 years ago, when human hunter-gatherers in what is now the Middle East began to develop a different kind of relationship with the grey wolves that followed their camps, scavenging for scraps. The wolves that were least fearful of humans, that came closest and proved most useful, were tolerated. Their pups were perhaps taken in, raised among the humans, and over generations, as the tamest and most cooperative animals bred with each other, the wolf became something new, the dog. The domestication of the dog was not a single event but a long, gradual process, a partnership that changed both species. Humans gained an ally of extraordinary versatility, an animal that could help with the hunt, guard the camp, herd other animals, carry small loads, and provide warmth on cold nights. Dogs gained a reliable food source and the protection of the most dangerous predator on the planet. It was a bargain that both parties, in their different ways, accepted, and the relationship has endured for 15,000 years, to the point where dogs are now one of the most numerous large carnivores on Earth. After dogs came the livestock animals. Sheep and goats were domesticated in the Middle East around 10,000 years ago, from wild mouflon and bezoar ibex respectively. Cattle followed, descended from the formidable aurochs, a wild bovine that stood nearly 2 meters at the shoulder and bore horns that would have impressed a modern bull. Pigs were domesticated from wild boar, probably independently in multiple locations across Eurasia. Horses were domesticated on the Eurasian steppe roughly 5,500 years ago, a development that transformed human warfare, trade, and communication across the ancient world as profoundly as the invention of the wheel. Each domestication was not merely a practical arrangement, it was, in evolutionary terms, a profound alteration of the domesticated species. Under human selective pressure, animals changed in just a few thousand years in ways that would have taken millions of years of natural selection. Dogs became more responsive to human facial expressions and eye gaze than any other animal, including wolves. Domestic cattle lost the aggression of their aurochs ancestors. Domestic horses became tameable and trainable. In every case, the process of domestication produced animals physically, behaviorally, and psychologically different from their wild relatives. And the numbers tell a stark story about just how thoroughly humans have reorganized the planet's mammalian biomass. If you were to weigh every mammal on Earth today, domestic livestock, cattle, pigs, sheep, goats, horses, and others would account for roughly 60% of the total. Wild mammals in all their diversity, every elephant, every wolf, every dolphin, every deer in every forest on Earth would account for approximately 4%. And humans ourselves would account for the remaining 36%. The transformation of the planet's wild places has been no less dramatic. The forests that once covered much of the temperate world have been cleared for agriculture. The great rivers have been dammed and redirected. The wetlands drained, the prairies plowed. And the wildlife that depended on these places has retreated, contracted, and in many cases disappeared entirely. Since the year 1500, roughly 100 mammal species have gone extinct, a rate of extinction several hundred times higher than the background rate seen in the fossil record. Some of these losses are well known. The thylacine or Tasmanian tiger, a marsupial carnivore that went extinct in the 1930s, the Beiji or Yangtze River dolphin last reliably seen in the early 2000s, the Caribbean monk seal hunted to extinction by the mid-20th century. Others are less famous but no less significant, the dozens of small island mammals that disappeared as European ships brought rats and cats to previously isolated shores. And yet amidst the losses, there are stories of extraordinary recovery, proof that the damage is not always irreversible. The humpback whale, reduced by industrial whaling to perhaps a few thousand individuals in the mid-20th century, has recovered to hundreds of thousands following the international ban on commercial whaling. The grey wolf has returned to much of Western Europe after being extirpated for centuries. The European bison, reduced to just 12 individuals in captivity by the 1920s, now numbers in the thousands, grazing in the forests of Poland and Belarus and beyond. The Arabian oryx was declared extinct in the wild in 1972, but a captive breeding program has since reintroduced it to its native range. These recoveries share something in common. They happened because humans chose consciously and deliberately to make them happen. That capacity to recognize a problem, to understand its causes, to feel something about the fate of another species, and to act is perhaps the most distinctively mammalian thing about us. It is, in a sense, the final expression of the same enlarged brain, the same social intelligence, the same capacity for empathy that evolved in the primate canopies of the Eocene, honed through millions of years of social living. We are the animal that broke the world. We are also, so far, the only animal capable of choosing to put it back together. We have traveled a long way together in this story. From the darkness and fire of 66 million years ago, from the ash-grey world of the first Paleocene morning, we have followed the mammals through forests of extraordinary richness, across grasslands where great herds moved like slow brown rivers, through the frozen tundra of the ice ages and into the complex, troubled, astonishing world of the present. Let us pause now at the end of this journey and look at what the mammals became. From those small, frightened survivors of the extinction, creatures you could hold in your cupped hands, the mammals have diversified into approximately 6,500 known living species, 6,500 different solutions to the problem of being a warm-blooded, milk-producing vertebrate on planet Earth. They span a range of body sizes so extreme that it barely seems possible within a single order of vertebrates. From the bumblebee bat, which weighs barely 2 grams and could sit comfortably on your thumbnail, to the blue whale, which weighs 200 tons and whose body alone contains enough blood to fill an Olympic swimming pool. They have colonized virtually every habitat on the surface of this planet. Polar bears patrol the floating ice of the Arctic, camels traverse the waterless heart of the Sahara, snow leopards move through the high Himalayas at altitudes above 5,000 meters, where the air is so thin that a human visitor would be gasping within minutes. Naked mole rats spend their entire lives underground in the dry soils of East Africa, never once seeing the sun. The star-nosed mole, whose extraordinary nose bears 22 pink tentacles containing more than 25,000 minute sensory receptors, hunts in the complete darkness of its underground tunnels, and the great whales plunge to depths that crush the hulls of unprotected submarines, navigating by sound through the perpetual midnight of the deep ocean. The mammalian brain is worth dwelling on because it represents something genuinely unprecedented in the history of life on Earth. The brain of an elephant weighs roughly 5 kilograms, and the elephant uses it to maintain decades-long social relationships, to navigate hundreds of kilometers of landscape from memory, to grieve its dead, to recognize itself in a mirror, one of the very few non-human animals that can do this, a behavior that most researchers interpret as evidence of genuine self-awareness. Elephants communicate across enormous distances using low-frequency calls, infrasound, below the range of human hearing, that travel through the ground as well as through the air, allowing family groups separated by many kilometers to coordinate their movements. Dolphins cooperate in ways that rival the complexity of human social behavior. They have been observed teaching hunting techniques to their young, wrapping sea sponges around their snouts to protect them while foraging on the sandy seafloor, a tool-use behavior transmitted culturally from mother to daughter across generations. Different dolphin populations have different vocalizations, different dialects in effect that identify their social group. They recognize individual companions by the unique signature whistles that each dolphin develops in early life, the equivalent, some researchers argue, of a name. The social complexity of mammals is one of their greatest evolutionary achievements. Wolf packs operate on intricate hierarchies of trust, loyalty, and cooperative hunting strategy, coordinating to bring down prey many times larger than any individual wolf could manage. Meerkats post dedicated sentries at the edge of their colonies, watching for aerial and terrestrial predators and giving alarm calls so specific that the group responds differently depending on whether the threat is a hawk or a snake. Naked mole rats, the only truly eusocial mammal, live in underground colonies of up to 300 individuals, with a single breeding queen and specialized worker and soldier castes, a social organization more reminiscent of an ant colony than a mammal society. And then there is the primate lineage, the line that leads through the Eocene forest dwellers and the Miocene apes and the Pliocene hominins to us. The human brain is the most complex object of comparable size in the known universe, at least in all the universe we have so far been able to examine. It contains roughly 86 billion neurons, each making thousands of connections to other neurons, producing a network of interconnections so vast that describing its total complexity meaningfully is beyond the capacity of any language yet devised. From this network has emerged music and mathematics, poetry and engineering, love and cruelty, the capacity for abstract thought and the ability to ask questions about the nature of reality itself. The capacity for consciousness, whatever that ultimately means, and we are not yet close to a complete answer, appears to be widespread among mammals, expressed in different ways and to different degrees across many lineages. The dog gazing at its human companion with unmistakable recognition and attachment. The elephant standing vigil over the bones of a dead companion. The chimpanzee watching a waterfall with an expression that primatologists have described cautiously as awe. Whether these are experiences comparable to human inner life, we cannot say with certainty, but they are not nothing, they are not mere mechanism. The story of mammalian evolution is, at its most fundamental level, a story about what becomes possible when a catastrophe opens the world. 66 million years ago, a rock fell from the sky and ended the age of one kind of life. In the rubble of that ending, another kind of life found its moment, small, warm, adaptable, socially connected, capable of learning and changing and persisting through whatever the planet threw at it. Every mammal alive today, every whale singing in the deep ocean, every bat navigating by sound through the dark, every elephant remembering the roots of its ancestors, every wolf howling into a winter night, every primate looking up at the stars is a continuation of that story. A living thread connecting the present moment to that cold, dark morning 66 million years ago when the world fell silent, and then slowly, tentatively, beautifully began again. This has been the story of the rise of mammals, and in one very real sense, it is also the story of everything that matters. And so, as you lie here now, let all of that settle around you like the quietest kind of snow. 66 million years of story slowly dissolving at the edges of your thoughts. The asteroid is gone. The dust has long since cleared. The forest grew back, slow and patient and green, and the mammals filled them, and the world went on and on and on right up to this moment, this bed, this breath, this particular darkness behind your eyes. You are the latest chapter in the oldest story on Earth. The same warmth that kept a small creature alive in a cold and broken world is keeping you alive right now, this very second, without you having to think about it at all. Your heart is beating, your blood is warm, you are against every conceivable odd here. Let that be enough for tonight. Let the mammoths walk slowly across the backs of your eyelids, through a quiet, snow-dusted landscape growing smaller and more distant with every breath you take. Let the whales descend through dark water unhurried, enormous, at peace. Let the forests of the Eocene rise up soft and green and impossibly far away. There is nothing you need to do now. There is nowhere you need to be. 66 million years of life led without knowing it to you, and you are allowed at last to rest.